Hi, I'm Prosita, and I'm going to be talking about our ASE 2025 published work, LLM-Assisted Synthesis of High Assurance C Programs. This is in collaboration with Ming-Hai Liu and Benjamin Delaware, and we all work at Purdue University in the Purple Research Center. So to begin with, I'd like to state what program synthesis seeks to do. It seeks to automatically generate a correct program that satisfies a specification of its behavior. Now, I want to elaborate on the present scenario of program synthesis with the help of this graph. Now, consider two axes where the x-axis represents the generality of the specifications and the y-axis represents the guarantees that the program the guarantees that we can give about the program meeting its specification. Now, when it comes to deductive synthesizers like Suslike and Synquit, they tend to be around this area of the graph. That is, they will automatically generate a correct by construction program that is a program that is fully functionally verified. But the range of specification that they can support is quite limited. And they internally tend to use some automated theorem provers like Z3 and CVT5 to generate these correct by construction programs. Now, LLMs these days are quite common owing to the large search space. So the programs generated by LLM would fall somewhere here in the graph, and which means that they would generate any program given any kind of specification, but it does not come with correctness guarantees. So we need to push the bar, and in order to push the bar, there needs to be significant verification effort. But we didn't quite lose the battle here because there exists theorem provers like ROC that helps us write theorems of this nature that states that given a specification that is a pre and post condition and the C program, you can write correctness theorems that states that the program satisfies the specification. But writing the theorem isn't enough. You also need to prove its correctness. And in ROC, you would involve the user, and the user would provide a set of tactics where each tactics advances the proof one step towards completion. And this whole proof is then machine checked. Once it passes all the tactics and we reach QED, and we are able to verify, which means that the program does meet its specification. But note that program synthesis aims to do this automatically. That is, it tends to automatically push this bar up. And that's what our tool SYNVER tries to do. It tends to automatically generate a correct program that is provide full functional correctness of its behavior for a diverse set of specifications. And it does so with a two-phased approach. The first phase being the generation phase, where a coder LLM is prompted to generate programs, and those programs are amenable to automated reasoning. The second phase, or the verification phase, that involves another LLM, which is the prover LLM, in combination with our symbolic reasoning engine to automate proofs of this nature. And this entire process is carried on inside Verified Software Toolchain, or VST, that takes programs, C programs, that can be compiled with COMCERT. COMCERT is a formally verified C compilers, giving us assurance of the binary that is generated. And it also allows us to write ROC proofs of the nature that we showed to establish correctness criterion of the program meeting the specifications. Now, given this framework, we will now dive into the two phases in more detail. Now, phase one is generate. As we mentioned, a generation phase comprises of prompting the LLM to generate programs that are amenable to automated reasoning. We do so by incorporating certain biases in the source space, and we call them syntactic biases. The first bias being, we ask the LLM to use programs that are recursive and not loopy, which means that, let's say this example here, there's an append function which says that to append L2 to L1, here the specifications are there and the program generated has recursion instead of loops. This is accepted by SYNVER. The reason that we do so is that if a program is generated with loops, it would need a loop invariant for the verification to go through. And loop invariants are often quite complex, needing user input, which is something that we want to avoid. Hence, by using this bias, we are eliminating the need of the user to step in and provide a loop invariant. The second bias that we use in the search spaces, we allow programs to call other functions. Programs calling functions are quite common in programming paradigm, but we only allow programs to call other functions who such that their specifications are available. If a function doesn't have a specification, we reject it. For example, this is a program that swaps and adds two numbers, and it calls to help. It makes two calls to the helper function add, and add here is not equipped with the specification. Therefore, even though the program is correct, SYNVER rejects it. Now, why do we do this? Because as similar to the loop invariant case, coming up with a specification for a novel function is very challenging, and that would also often require user input. And we don't want that. We want to automate this process. Therefore, placing these syntactic restrictions in our search space moves us a step closer towards automatically constructing these programs that meet the specification. Now, given this information, we construct an initial prompt to the Coral LLM. The prompt comprises of the bias description, some examples of C programs that maintain the bias, and the specification at hand. Now, the specification comes in three categories. First, the formal. Second, a natural language description. Third, a couple of input-output examples. Now, with the specifications and the biases and examples at hand, we prompt the Coder LLM. The Coder LLM will generate a candidate C program that is then subjected to the syntactic checks. If the syntactic checks succeed, a candidate program is generated and we go to phase 2. If it fails, that is, if there is a syntax error or a violation of our bias, we reprompt the Coder LLM with the appropriate error message and the specification. Now, this loop continues till we either produce a candidate program or the Coder LLM times out, which results in an unverified C program. Now, this is the generation phase. Next, we move to the verification phase. Now, in the verification phase, we assume that we already have a candidate program, and phase 2 is equipped with the formal specification at hand. Now, as we said before, phase 2, that is verify, combines our symbolic reasoning engine, which we call SEPAuto, and a prover LLM that predicts tactics to advance the goal. We also develop a set of heuristics that either selects or rejects the tactic that is proposed by the prover LLM. Now, let's look into the workflow of this phase in more detail. Now, we are assuming that a candidate program has been generated from phase 1. Now, the candidate program is converted into a shape of into a goal that is amenable to reasoning inside VST. It is at first sent as input to SEPAuto. Now, SEPAuto will attempt to either completely verify. If it is able to completely verify, then we already have a certification of the program. And in that case, we don't need to call prover LLM at all. But if it is not able to verify and it simplifies or decomposes into n subgoals, each of these goals are then sent to the prover LLM, which is then equipped with an initial prompt that comprises of a set of example VST proofs, that is how proofs of programs look like in VST, the specification at hand, and the program. The prover LLM then takes the first goal and then predicts a set of 5 tactics in order of success. The order of success is determined by the LLM itself. Now, each of these tactics are then subject to heuristic checks in this order. Now, here we see that tactics 1 and 2 fail the heuristic checks because tactic 1 makes the goal too complicated, and tactic 2 results in the goal not making any progress or not changing at all. Tactic 3 succeeds the heuristic checks, changes the goal, and then it's sent back to SEPAuto. Because tactic 3 succeeds, we discard tactics 4 and 5. Now, SEPAuto will first attempt to fully verify this goal. If it is unable to do so, it can also time out that results in a partially verified C program, or it can further decompose this goal into multiple subgoals, and each of these subgoals will be sent to the prover LLM with a reprompt stating the current goals, the generated proof, and ask it to generate a fresh set of tactics. Now, it can also happen that all the tactics that are predicted by LLM get rejected by the heuristic checkers, citing their reasons. Now, in this case, we don't have anything to send to SEPAuto, so we reprompt the prover LLM from here with the current goal, all of the failed reasons, the generated proof, and we ask it to generate a fresh set of tactics for the current goal at hand. Now, there can also be a third case where the prover LLM can say that this goal is an error goal, so it is unsolvable. In that case, we have a backtrack engine that will select the parent of the current goal and will reprompt the prover LLM with the failed reason, the parent goal, and the generated proof, and ask it to generate a fresh set of tactics for the parent goal. Now, this entire process continues till you either fully verify the program producing a certificate, or you time out and then you have a partially verified program, the proof of which is then available to the user to investigate. Now, let's move to the evaluation. We evaluate SYNVER on 3 domains of synthesis. And for each of the domain, we hand construct the specifications in VST. The first domain being basic, it comprises of 19 benchmarks, and all of them use the data structure arrays and primitive types like int and char. The second being heap manipulating programs, again, 24 benchmarks, and they use linked lists, trees, and arrays in combination with them. The third being API, 5 benchmarks here, and here all of the programs are constructed by calling other functions which are equipped with specifications. To summarize, the generation phase performs 100%. That is, we don't need to reprompt at all. All the programs are generated correctly, biased correctly at the first try. SYNVER also achieves a reasonable amount of success in proving. That is, the verifier does a good job, fully automatically verifies 70% of the programs. But it does need reprompting, but it does show promise in automatically verifying. We also have a detailed evaluation on the wall clock time, prompt components, and prover comparisons that are present in the paper, and that we will discuss a little bit later. We note that GPT-5 Mini is used here for both the prover and the coder LLM. So to conclude here, SYNVER is the first general purpose synthesizer for high assurance C programs. And the reason it works is because of our 2 key ideas. The first being we impose these syntactic biases for generating recursive code and only calling functions whose specifications are available. This would reduce human effort. And the second being our prover, which is a custom hybrid reasoning engine. Our evaluations show that SYNVER automatically verifies majority of the program, making it a suitable candidate for program synthesis in general and making it applicable to different domains of synthesis. Please check our code base out. And if you're ASE, check our poster out. We have an artifact published, and please feel free to contact me at the email listed. Now, coming into some backup slides, these are sort of emphasizing SYNVER's performances in more detail that I wasn't able to talk about. So this slide states the wall clock proof generation time. I'd like to know that the program generation time is fairly constant. It takes roughly 10 seconds to generate each program. And since our programs didn't really require any reprompting in the generate phase, yeah, they're fairly about 10 seconds. As we see that for the proof generation time, here the light brown boxes represent the fully verified program, and the gray boxes are the partially verified program. As we expect that the partially verified programs take much longer than the fully verified ones, because they will reject multiple tactics and will be evaluated or will be attempted to be proven till the prover LLM reaches its timeout. We also see that we achieved the most success in heap manipulating programs. The reason is that the heap components are resolved with fairly powerful tactics that VST is already equipped with. The second slide here being the percentage of discarded tactics. This is the result of this is proportional to the wall clock time, which means that the partially verified programs have more discarded tactics than the fully verified ones. We note that in the fully verified case, specifically for the basic and heap cases, the number of discarded tactics percentages are 0 till medium. So that's really impressive. That states that SYNVER tends to not discard a lot of tactics for the fully verified ones. Now I'm going to be going to the paper real quick to show some more details. Okay. So at first here, I'd like to talk about what SEPAuto, our symbolic engine, does. So this is built with the set of tactics that VST already provides with some more standard rock tactics. What it tries to do is try to sort of automate the forward analysis with the help of the tactics that is already quite powerful and that are provided by VST. So I'm just going to be going through some of the cases here. So in this case, it at first it looks at the shape of the goal. If there's an if then else statement here, a VST already provides a tactic called forward if that will help it make progress. So it looks at the shape of the goal, it sees that there's an if then else. There's no need to query an LLM here. I'll just invoke the forward if tactic. In the second case, if there's a statement that follows the if then else block, in this case, VST would expect a joint post condition. That is a specification, a post condition that will satisfy both the then and the else branches. So we, as I said before, we would like to eliminate the user input or as much as possible. And here, inferring a spec is a hard problem. So that would want a user input. But what we do here is we change the goal a little bit. We push C3 inside both the then and the else branches. And in this case, now it is amenable to automated reasoning with the forward if tactic. Next, if there's a function call here, we need to infer what these parameters are, and VST has a strict rule of the order of parameters being exactly in the order of specifications. Now, the specification need not be the same as the order of the parameters here, as the specification also contains the underlying mathematical representation of the data structure as well as the share permission. We do have a set of heuristics, and we designed an inference procedure to infer the set of parameters. I'm not going to go over that in a lot of detail, but once this inference procedure returns a set of parameters, we invoke forward call with this set. In the other cases, if it is something else in a standard separation logic triple, is going to try to move forward with some automation. Those automation are again very limited, like some null pointer checks or some very basic intelligent reasoning, and it would keep trying to make progress. And once it is not, it is going to query the prover LLM to do so. This is GenProof. This is what the entire prover engine or the verify is based on. This is going to, at first, after the tactics are predicted, it's going to try to make progress using text step, which evaluates the heuristics. When we go through the heuristics here, the heuristics are presented here. So as you can see that at first, it checks if the current tactic has already been tried. If it was tried before and it failed, we don't try. So we reject it. The second here, it then asks if it's not tried, it applies and it sees if there is an error, if the tactics results in the goal being an erroneous one, or the goal doesn't make progress, as we saw, then it's also rejected. Then it also checks if the goal was involved in a cycle. In that case, it's also rejected because we don't want to visit the same goal twice. And then regarding the complicated goal becoming too complicated, we check the size of the conclusion of the goal. And if it is more than twice the current goal, we reject it. So these are the set of heuristics that we have. And if neither of the situations are there, then we consider it successful and we invoke the tactic, and then the results of the tactic are sent to SEPAuto. These are our set of heuristics I was not able to cover in time. These are, again, the different prompt templates, which I briefly discussed. They're all there in the paper. So now I'm going to be talking about some of the results of the table. As you can see, this table 1 is about the fully verified benchmarks. Table 2 is about the partially verified. As you see here, GT is the program generation time. There is less variation here. PT is the proof generation time. If you see, the partially verified ones are quite faster than the fully verified ones. That's what we saw in the bar charts as well. So now here we did some manual inspection of the partially verified benchmarks, and I'm just going to talk about what we observed, why it caused the prover LLM to time out, even though all the programs were produced were semantically correct. The first reason being a lot of discarded tactics. This is due to faulty suggestions. The tactics proposed were erroneous or couldn't make progress, so the heuristic checks failed. The second being cyclic reasoning. Now, this is where the heuristic checks succeeded, but then the sort of sequence of tactics were applied in a way that a previously seen goal was met again, but they were sort of syntactically different, but semantically same. So we have cyclic reasoning, but it could not be caught by our heuristics because they were syntactically different, but semantically equivalent. Third being superfluous tactic suggestions. Now, this is a limitation of our heuristics blow up. So blow up checks the size of the goal. But here, if you have unnecessary tactics like nested induction or induction followed by destruct, that would also complicate the goal. It need not increase the goal by 2x, but it would also complicate the goal. The last one being backtracking failure. As we mentioned, that we only backtrack one level up, that is to the immediate parent, but it happened for 3 of our benchmarks, it incorrectly instantiated an existential variable. And in that case, since we just backtrack one level, it was too late in the proof tree when it decided that the goal has indeed become unsolvable. It's an error goal. But then going up too many steps was increasing the sort of the timeout threshold. So it timed out. So these are the combinations. At first was our heuristics working correctly, but the tactics produced were a lot in violation of the heuristics. The others being, yes, the heuristics were not clever enough to catch them. And they can be mitigated by further improving our heuristics to specifically catch cyclic reasoning on semantically equivalent goals, to sort of make the blow up tactic more smart, to sort of catch complicated goals rather that do not focus on the size. And the last being backtracking to an arbitrary point. So these are things that can be improved. So now let me talk about the research question 2, where we investigated the different prompt components of the coder LLM. So as I said before, the coder LLM is equipped with the prompt of the coder LLM equipped with the biases and the different forms of the specifications. So here we decided to at first not give the biases, give everything else, then one by one not give the specifications or give the specifications in a subset or a proper subset of the form that was already there. And what we observed was P1 that didn't mention the biases. LLM tends to generate programs with loops unless it admits a naturally recursive function. So here we see that out of all the programs were generated with loops other than 4. And I believe there's 20 something with loops. And out of the 4, 3 admit naturally recursive solutions. So which means that they do tend to naturally generate programs with loops. Hence we need to incorporate the bias in the prompt. And with respect to the different modes of specifications, so these are from P2 through P5, we observe that LLM responds most positively to natural language. It is kind of don't care for the examples, and regarding the specifications, it often gets confused with the separating conjunction and separating implication operator. So that makes us conclude that it's not that well versed with separation logic or how the operators look like or work, but it most positively responds to the natural language description. Now, the last set of experiments that I'd like you to look at is the prover analysis. So we do compare our prover, that is GenProof, which is the combination of our SEP Auto, which is a symbolic reasoning engine, and the prover LLM with the heuristics. So we do compare this with various other frameworks. So the first two being Rango and Tactician. These are the state-of-the-art learning-based ROC theorem provers. SE being just the SEP Auto, no theorem prover, no prover LLM involved. These two, GP minus SA minus H, GP plus SA minus H, being the different forms of GenProof with limited heuristic support, and SA++ being a roofline overfit automation tactic designed by a verification expert. By overfit, I mean that overfits to the set of benchmarks. So we observed that the state-of-the-art learning-based theorem provers for ROC like Rango and Tactician underperform for these set of benchmarks. Hence, sort of pushing out theories that we need a special purpose theorem prover to do proofs of this kind. Now, among the variants of GenProof, we see that GenProof is the most general purpose one. And excuse me, is the most general purpose one. SA itself is quite powerful. It performs better than Rango and Tactician here, showing that even a tactic that is designed with very limited intelligence and shape level automation is more powerful for this set of benchmarks than Rango and Tactician. And SA++ is again a roofline tactic that is designated for just benchmarks of this kind, but still we can see here that GenProof does outperform better than SEP Auto plus when it comes to sort of inferring and proposing new lemmas that SEP Auto plus cannot do because it's manual. Hence, from this set of experiments, we do conclude that approval like GenProof is indeed needed to verify C programs of this kind, and we do need a specialized prover and generation engine to indeed verify end-to-end high assurance C programs of this fashion. Yeah, so this is what the sort of other experiments are that I couldn't discuss in the main talk due to lack of time. Yes, if you have any further questions, please feel free to contact me here at this email address. Thank you so much for listening.